share my screen over here and plug in my screen, and there we go. Okay, we are welcome to another data mining class. I'm sure you're all distraught, but I apologize for my 2 minutes tardiness in getting my stuff set up. Everyone who's here gets to have an opinion on the date for the next quiz. My suggested date is next Monday, October 10th. But if you all would prefer a different date, then you can tell me right now, and I'll type in something else right here before pressing comment. Again, this quiz is on the quiz practice handout that I had last time. It's all the definitions of the VC dimension stuff, shattering, and that kind of stuff. Wednesday the 12th. Also vote Wednesday. Wednesday 12th. Anybody else strongly opposed? Push it back farther. Even closer. Have it right now. No. To beat the people who aren't here right now. Okay, there we go. Wednesday the 12th. And then last time, so the notes for today, there's a new folder for learning from data, linear models. We're about halfway through the material that I'm hoping for us to cover this semester, which is good since we're about halfway through the semester. So we're on track for there to be so much stuff to study for the final and all the other midterms, which I'm sure everyone's thrilled about. The notes that we went over last time, or that I gave out last time, was this chapter 2, training versus testing, part 2. And there's 2 problems with a number of parts on here, but this is the first thing that's really got the practice midterm sort of questions on it. But this first problem is going through a bunch of VC dimension calculations. And we went through some of those last time at the end of class. And again, all of these come from either the textbook actually gives them to you, like what the answer is, or it's a slight variation on the one that the textbook gives you. And it's one of the problems in the back of the chapter. So if for whatever reason you don't feel like you're 100% comfortable with doing these problems, the textbook, example 2.2 on these pages right here, great place to look for references. Where we left off went to this problem 2 down here, which has a bunch of either prove or give a counterexample sort of statements, and a very good chance that there'll be a couple of these in sort of a free response form on the midterm, and a couple of these in a true false open sort of section on the midterm. And so let's go through a couple examples right now about how to work these problems. This first one right here. Well, first, let me say that what I think is the hardest part about these problems is just actually understanding all the definitions of these problems. And so once you have all the definitions memorized, again, for the quiz on Wednesday, then working through these problems should be hopefully relatively easy, that all of these things follow immediately from the definitions, and that if you really understand the definitions, then all of these things will be, I'll say, trivial, in the mathematical sense of trivial, where which has nothing at all to do with what ordinary people think trivial means, but means that it follows directly from the definition. And conversely, working on these problems will help you understand a little bit more about maybe some of the motivations about why things are defined the way they are, because this explores the edge cases of those definitions. And so we'll make it a little bit easier for you to memorize these. All those definitions. And so I recommend before the next quiz, before next Wednesday, having tried to work through everything in this notes packet here, even though these questions won't be on the quiz, that'll help you prepare for the quiz and vice versa. Okay, so this first problem, the things to note about this first problem, it's asking, saying, let f be the true labeling function. How many people here know the definition off the top of your head of the true labeling function? Okay, I do. So let's write it out. Good thing to do on these sorts of problems is just like write out the definitions of all the stuff that appears. And so f is going to be equal to the argmin of E out of H, where H is contained in this H star thing. And this H star, what it means is it's like the set of all possible hypothesis classes. And so the intuition here is that this is f is somehow the best possible function. No matter what hypothesis class you were to choose, then this f is the best possible function we can get. So that's the first part of this, just this let f be the labeling function. And then it asks then for all data distributions, is it the case that this E out of f equals 0? And the answer here goes back to a long time ago, we discussed that there's 3 possible ways that a machine learning algorithm or a data mining algorithm can fail. And I drew 3 examples. One is when we have data that's somehow easily separated, but we just pick a really bad hypothesis like this. We know f can't possibly be this bad hypothesis because f is the best possible hypothesis. So we're not in a situation, we're not asking about a situation like this. The other is that if we had data that looked somehow like this maybe, and so this data on the left over here, this is linearly separable data because I can draw a straight line to separate it. Maybe I'll actually draw the f function here in green. That would be the f function. And here, in this particular case, we would have that the E out of f equals 0. Again, the E out is our error on the testing data, on like unseen data that you haven't. If you had infinite amounts of unseen data, what would your error be? And here, the intuition behind this picture is that all the pluses are to the left, all the negatives to the right, no matter what. And so if we were to pick a hypothesis in the middle, then our true error would be 0. So that's one possible source of error. That one agrees with this statement so far. So things are looking good so far. The second possibility over here with this circle, the things are no longer linearly separable. If I'm using the perceptron hypothesis class, no matter where I draw my straight line at, again, the book uses G for these values here. These are the actual hypotheses that you've somehow learned from some sort of algorithm. And we've, no matter what possible straight line I draw here, we can't separate this data. So E out of G is guaranteed to be bigger than 0, no matter what learning algorithm I'm using. But there is still some other hypothesis class of like circles, like that. If that was F, then we would still be perfectly classifying our data. And so the E out of f would still be equal to 0 in this case. We haven't talked too much about this particular hypothesis class right here of circles and circulating data, but that's one of the things that you'll have to be able to calculate the VC dimension for in the problem above. And the book also works through that. So that's a good one to know, another alternative to the perceptron there. And then our last possible source of bad things happening was that things we had a data set maybe that seems mostly separable like this, but somehow for whatever reason there's, do this in orange because I haven't used that color yet, there's some like bad examples, some misclassified examples, some positives where the negatives should be and some negatives where the positives should be. And in particular, that each label or y value has some noise associated with it. And so that the y sub I was defined to be f of x sub I, the y sub I being the plus or the minus, how we decided to label the data point, the x sub I being the like location in the coordinate plane where the data point is located. But then there's this like random probability distribution, that epsilon right here, that's the noise. And no matter what f you draw, there's just no way to account for this noise over here. And so if that is my f, that's still the best possible function, but there's no way to account for these noisy labels, these negatives and these pluses that have just somehow randomly been flipped by this noise. And so in this case, the E out of f, and my handwriting right now is really bad, is strictly greater than 0. And it's equal to the amount of noise that we have. And so this statement up here, because of this third type of error possibility in our data set, this statement up here is false. Any questions about any of that so far? Yes, no.
So the circle one doesn't mean it's false.
Yeah, so here, in both neither of these two cases over here are counterexamples, because the f function that I was able to find some sort of decision boundary that would have a 0 true error, a 0 E out. In this case, the decision boundary is a circle. And if we were limited to the perceptron hypothesis class, which can only draw straight lines, the perceptron hypothesis class must have some E out bigger than 0. So here, in this case, E out of G guaranteed to be greater than 0, no matter what algorithm I use for G. Over here, there are some G's that will have 0 E out, some G's that will have greater than 0 E out. But there might be a good algorithm that you could use, which will get you the 0 E out. Here, there's no possible algorithm, no possible way of selecting G that can get me the zero testing error. But if I expanded my hypothesis class to include these circles, then I could get the E out equals 0. So this is not a counterexample to this statement over here. The only counterexample is actually when you have noise in this labeling process.
Why did you not just like draw a line to go around?
Yeah, it's a great question. So the question is, or the suggestion is that maybe my hypothesis should look something, I'll draw it in, let's see, red. My hypothesis could look something like, try to carve out all these pluses and minuses. Oh, and let's capture that +2, something like that, some sort of crazy shape like this. And for the training data, so what I've visualized here is just the training data, that would work. You would be able to get a 0 training error. But what's important here is that we're talking about the E out being greater than 0. And for the E out being greater than 0, we're talking about all possible data sets as the amount of data goes to infinity. And as the amount of data goes to infinity in this exact same spot right here, like wherever this minus is, if we had infinite amounts of data, there would also be a data point with a plus right here too. because of this noise. And so there's no way to separate that individual spot right there that's sort of both a plus and a minus. Yeah, it's hard to visualize because it's hard to visualize an infinite amount of data. But the idea is this E over here is just randomly flipping these points. And so even though you can carve it out for the training data, there's no way to carve it out for the actual testing true data. So this would be an example right here. This red line would be an example of overfitting the data. That's a key vocab word that will sort of formalize eventually, but we haven't formalized that yet, but this is an example of overfitting, if you've heard that before.
Two questions.
Sure.
First one is, so are we considering F to be a ground truth function, or is that different?
Yeah, so this F function has a lot of names that are all totally equivalent to each other. Here I'm using the true labeling function. That's one the book uses the most. Ground truth, also sometimes used. The Bayes error function, the God function, the universe function, has all those names used by different communities and authors to mean the same thing. Somehow, like whatever the best possible thing is.
Okay. Yeah, I'm kind of having trouble wrapping my head around the fact that I feel like using like this idea of like the ground truth function, like, why are we getting an error greater than zero? Like basically the test of data, like why are we getting an error greater than zero?
Yeah, so the question is somehow if F is the ground truth, how can it not be perfect? And so if you think about our example with you're a bank and you're providing loan like information, and let's say we only have two features here. It's two-dimensional, and so your two features are the income of the applicant and their net worth. And no matter what possible decision function you create out of the income and the net worth, there's no possible way that you can figure out if the person's going to default or not default on a loan, because we just don't have enough information available. We're not able to take into account like future things that might happen, like they get fired from their job or other things that impact the loan application process or the default rate of the loan. And so F is like, it's the ground truth, but it's also the ground truth just with like the limited features that you have available. The universe might have more features available to it. And so it might be, maybe the universe actually is deterministic on whether somebody defaults or not. That's a philosophical question. But whether the universe is deterministic or not deterministic, we don't have access to all the information the universe has access to. And so our F function, our true labeling function, is guaranteed to have this zero output, this non-zero true error.
My second question is, so we see like the epsilon, like the noise, as like a random variable, so it can be like normally distributed.
Yeah, so in this case, this noise, yeah, the right way to think about it, the most formal way to think about it is that it's a random variable. And so that leads to a question, what's the distribution of the random variable? Well, here the yi's have to be positive or negative ones. And so the distribution of this noise also has to be like some sort of distribution over positive and negative ones. So yeah, people who like on the very extreme end of theoretical machine learning or sort of the middle range of statistics in terms of theory fret a lot about like, okay, I'm going to assume that the noise is generated by a Gaussian distribution. How does that affect my training error or my true error? I'm going to assume that the noise is generated by some distribution. Now what can I do because of that assumption? In this class, and for the most part, machine learning and data mining in general, we don't make any assumptions. We don't really care. Oh dear, we don't care about what that noise is. We just there's some noise, and we want to be able to make statements that hold true no matter what that noise looks like. And so in particular, the VC dimension bounds, they hold true for any possible noise distribution that we have. These are all fantastic questions everybody's asking. Any other questions about this problem or related things? Okay, in terms of what you might like have to write for an exam to get full credit, I mean, the main thing here is getting the right true-false answer. But in terms of like, yes, if it's false, then the right thing to do is think about a counterexample and provide that counterexample. How formal do you have to be in that counterexample? Well, if you said it was false because there can be noise, that would be a full credit thing. If you said false and drew a picture like this trying to illustrate the idea of noise, that would be a full credit thing. If you said false and then actually like provided me a concrete noise distribution, that would be a full credit thing as well. Somehow like explaining why it's false. And basically as long as you don't say something incorrect, I'll be generous in grading that. Okay, number 2. Moving on. So here we have H as the perceptron hypothesis class and G the result of the perceptron learning algorithm, the only algorithm that we've actually seen so far. And F also our true labeling function. In the book's notation, F is always going to be the true labeling function, but I will always try to remind you of that in these statements here, because otherwise, I know it seems weird to me just to have an F by itself. The question here is it guaranteed that E out of G is greater than or equal to E out of F? Anybody want to volunteer a guess? Why?
Yes, no, true, yes.
True? 2 truths? Anybody? So why true?
Because H, the perceptron hypothesis class, is a subset of all the possible hypothesis classes, and F is defined to be the best out of sample error for all the hypothesis classes.
Yeah, it's true, and it's basically immediate from the definition of F again up here. That so again, I'll write it out. F equals the argmin of H in H star E out of F, and then I'll also say that the perceptron, we'll say H perceptron is a subset of H star, and both of those things together imply that the statement that we're looking for, E out of F less than or equal to E out G. Because if G were possibly like whatever the best possible G is, whatever the best possible perceptron is, that's inside of H star, so that F has the possibility of being that. It can only be better. This is, yeah, you wouldn't have to write out all these formulas to get full credit, just somehow saying that any of the things that have been said would work as well in a less formal way. Any questions about this problem? Okay, do a couple more, but let's skip down a little bit to things a little bit different. Let's go down to number 7. The VC dimension of every finite hypothesis class is finite. Anybody want to venture, I guess? True, false, open? We know it can't be open. We haven't talked about any open problems related to this statistical stuff, VC dimension. So it's not open. It's either true or false. We've seen at one point to the very, very briefly and in passing, the VC dimension of a finite hypothesis class turns out to be equal to dVC of H, where that's finite, is equal to O of log M. And here the m is the notation again for the size of h in the book's notation. And so if the hypothesis class is finite, then the VC dimension also, that means that m is finite. So this whole thing over here is going to be finite. So that is going to be true. This big O right here is in fact, like, you can't make it a theta. It must be O. There are finite hypothesis classes of arbitrary large size with constant VC dimension. But the biggest it can possibly be is log of m. I think in the textbook, they give the exact formula, which something like log base 2 of m plus maybe a weird constant. Any questions about number 7?
So is that true all the time, or only like if it's infinite, is that also true?
Yeah, so the question is this: would this statement that I have here written in red be true if H was an infinite hypothesis class? And it would actually be true, but it would be trivial. That if H over here was infinite, this M over here would be infinite. So the log of infinity would still be infinity, and O is an upper bound. So it's just our upper bound on the VC dimension can't be any bigger than infinity, but we already knew that, can't be any bigger than infinity. But again, because this is a not necessarily tight upper bound, it's just the big O, the things can be, the VC dimension can be finite even if H is infinite. Did that answer your question?
Okay. So, okay, so A would be false, right?
Yeah, so here, question number 8. The VC dimension of every infinite hypothesis class is infinite, and the suggestion was this is false, and that's correct. The entire point of VC dimension was to have some sort of measure of the size of infinite hypothesis classes that would be finite in size, so that we can get bounds on the generalization error. And a concrete counterexample for this would be that, again, the perceptron has the VC dimension equal to theta of d. This is an infinite hypothesis class over here, but size finite, theta d. When we were working only with matrices, we were saying that some good things to consider with matrices when thinking about counterexamples are like the most simple possible matrices, like the identity, the zero matrix, the one matrix. When you're thinking about hypothesis classes, good hypothesis classes to consider are the perceptron, if you're thinking about infinite hypothesis classes somehow, or if you're allowing finite hypothesis classes, then there's the list that I gave you in a previous, maybe 2 notes packets ago, that had a list of finite hypothesis classes. Any questions on this problem?
So when you say the perceptron has like VC dimension theta d, is the perceptron an infinite hypothesis class?
Yeah, so let's remind ourselves the definition of the perceptron. It's H equals the set of X mapping onto the sign. I didn't ask you all to memorize this, but this is one that you're just going to have to write out so much that there's no way you're not going to have it memorized here in a little bit. W contained in R to the D. If you want to explicitly memorize it, then that would be a good thing to do so that you can think about for these counterexamples. And here, so like, why is this an infinite counterexample? Well, this W weight vector here can be any possible vector in R to the D, and R to the D is an infinite set. So the size of H is the size of R to the D, which is a very infinitely large set. Good question. Any other questions? Okay, then we're going to move on to today's note packet, and a couple sort of preamble things about this note packet. The first one is that if I had to pick like one single topic that is the most important topic of the entire semester, this would be it. And the reason for that is that this is going to be giving us like the first really extremely practical tools that we'll have for solving like real world data mining problems. Everything that we've talked about the last 2 or 3 weeks, everything since the first midterm, has been pretty abstract, and that's one of the main difficulties of it, is how abstract it is. Like this idea of VC dimension of infinite function spaces. Oh my goodness, what does that even mean? This is why we care about all of that, because we're going to be doing clever things in this set of notes in order to manipulate our VC dimension in order to get the optimal statistical properties that we want for our particular situation. Last set of notes ended in chapter 2. Now we're jumping ahead up to chapter 3.4 here. So skipping a little bit, we're going to come back to the stuff in between, but we're skipping ahead to this so that you'll be able to do your next programming assignment. This will be the last set of new material that we'll need for the actual like coding stuff. So again, up here at the very beginning, we just defined this perceptron hypothesis class on the previous notes. And the most important thing, like if you remember one thing about it, it's that the VC dimension is theta d. And we care about the VC dimension because it controls our generalization error. What we're talking about in this section here is a feature transform or a feature map. And that's what's defined here in definition 1. Anytime you see this symbol right here, this is a capital Greek letter phi right here. And phi in the textbook and the vast majority of data mining, machine learning literature, phi is one of these examples of feature maps or feature transforms. The textbook says feature transform. I like feature map better because it's fewer syllables, so it's faster to say and write. So I'll probably say feature map more than feature transform, but it's the same thing. And the idea of this phi function, so it goes from r to the d right here to r to the d prime. In the textbook, they introduce that the domain of phi is x, like a super fancy script x thing right here, and that the range over here is a super fancy script z thing. They don't actually do anything special with that though. X is always r to the d, and z is always r to the d prime. So I just skipped that right here. And we're going to be applying this phi function to all of our data points, somehow transforming them into something different so that we'll be in this r to the d prime feature space instead of the r to the d original data space. That's, again, still pretty abstract. We'll be getting more concrete here in a little bit. But first, this note that the textbook, at least at this point, only talks about feature transforms, feature maps. If you look almost anywhere else, like documentation in scikit-learn, which you'll have to be referencing for the next assignment, they talk about kernel transforms or kernel functions. And that kernel function is something that we'll talk about later, exactly what the difference is between kernels and feature transforms. But it's essentially the same thing. There turns out there's a bijection between kernel functions and feature transforms. So people use the two things interchangeably. And if you ever see somebody talking about kernels, this is exactly what they mean. They mean this phi function right here. And what we're using this phi function for is building this modified hypothesis class right here. And the important thing here is to pay attention to the difference between equation 2 up down below and equation 1 up above. This phi function right here, this phi function is being applied to our data points x so that it's mapping the data points into the feature space and then doing the perceptron in this new feature space. And so our W weight vector is now in this D prime space over here, D prime, instead of the original D space. And by choosing a good phi functions, we can manipulate exactly the statistical properties of this and get good results. Okay, we're going to get more concrete here in a second, but before that, any questions? Yes.
There's the feed function, so like the data is in a more like readable or applicable format for like Perceptron or whatever file you're using.
Yeah, so sometimes we'll be using the feed function to increase the dimensions. We'll see that that will make training easier, get a better training error. Sometimes we'll be using the feed function to decrease the dimensions, and we'll see that that will give us better generalization errors. And so exactly like what function we choose will depend on what why our algorithm is not performing as well as it should be. There's two examples of, let's see. So most of these feed functions they're in like many dimensional spaces, very hard to visualize. But there's two functions that are like the prototypical visualization functions. And I have these links to YouTube videos we'll take a look at here in a second. They're just short, like 20-second clips visualizing these example functions. But before doing that, we're going to draw some pictures. So here, this is one of the bad error cases that we saw before, talking about the examples of how learning can fail. That if we have this sort of circle-looking data, then there's no perceptron that can classify this well because there's no linear line that can separate this. But it turns out that if you apply a really clever feature transformation, and that feature transformation would look like, so phi, this is my version of the capital phi of x equals x1, x2, x1 times x2. These two features over here are the original features. This feature over here is a new feature that we've added, or that we've constructed. And it turns out that this decision boundary of E sub f this circle function right here, that g is contained in h of phi with this particular feature map. So again, this h phi is defined up here. It's the perceptron classifier, but we've done this to the data. And sometimes you'll hear people say that we've augmented the data with this new feature over here, which is the product of the original features. Why this is the case is not at all obvious, but there's this really classic visualization that we're going to go to here, which will hopefully help explain why this circle is now inside of h sub phi. So I'm going to switch over to YouTube, have the video opened up right here. And it's gonna, so here, this data set right here, the colors are a little bit hard to see, but there's a bunch of blue things in the middle and red things on the outside. And so the blues are like the pluses and the minuses that we're trying to differentiate. And after, this is the original data space right here. When we apply it, we go from a two-dimensional space to a three-dimensional space. And in the third dimension, everything gets lifted up by this parabola sort of shape, because the product of two variables makes a parabola, makes a quadratic. And now in this three-dimensional shape, a linear separator, a perceptron, is not a straight line anymore. It is a plane. The perceptron always somehow divides our space in half, whatever shape it needs to be to do that. And now in this third, this sort of lifted up kind of manifoldish thing up above, all the blue things are below this purple line, this purple hyperplane, and all the red things are above this hyperplane. And so by slicing it like that, we get this linear separator. And now they're projecting it back onto the two-dimensional original data space down here, and we get that circle. When I was first learning about feature transforms, it probably took me like a dozen watches of this video before things like finally really clicked for me. And so if it takes you a dozen watches of this video, then you are, if not in good company, in my company. Any questions on, yeah?
Does that mean all the red dots are either above or below the blue dots? Then?
After they've been transformed this way, then yeah. Yeah. So, I guess technically this line looks like, or this hyperplane looks like it's at a little bit of a slant right here. So this red dot right over here is not above this blue dot way over here. But the red dots are all above the hyperplane and the blue dots all below the hyperplane. But the hyperplane doesn't have to be a horizontal line, just any sort of, just like in 2 dimensions, our line could be pointed in any possible direction. In 3 dimensions, our plane can be pointed in any possible direction. Good question. Any other questions about this example? Okay, the second example, another classic, is sometimes called the Xor example. And so here are my axes, and let's draw some pluses over here like this, and pluses over here, negatives, negatives, like that. And again, there's no individual line that you can draw that is going to separate these things out from each other. But if you use the feature map, be closely related to the other one, but a little bit simpler even, of just x1 times x2. That's supposed to be multiplication, not a semicolon. Then you'll be able to separate these things out from each other. And actually drawing what the possible separators are is a little bit difficult, but if we come back over here into this YouTube video and take a look at this, so that's our original data space right there, the greens and the reds. And when they apply this transformation, it maps everything down into sort of taking those opposite quadrants and merging them together. And now something like this can be linearly separated. Turns out that, get the years right on this. So the perceptron was invented by a guy named Rosenblatt in 1957, and everybody was super excited about it for a while. It was solving all sorts of cool problems. But then there was a famous, it was called AI winter that happened, where, and this is from 1974 to 1980, where everybody just stopped funding development into artificial intelligence or machine learning or data mining, any of these sorts of fields. And one of the reasons was because people were coming up to the limitations of this perceptron, what it could do and couldn't do. And this is the most famous example of the limitations of a perceptron, this Xor problem. There's a very famous book published just about how the perceptron can't solve this problem. And so all the funding agencies, Microsoft, like these companies, Department of Defense said, okay, no more money for for machine learning research because we're not making any progress. And it's just that nobody had thought of this particular like feature embedding yet, this kind of simple thing that whether you think it's obvious or not in retrospect, it's certainly simple compared to the things that we're doing now. And so for this period down here, we were in this AI winter period because nobody was funding machine learning nobody's funding AI because of this particular problem. Today, so this note I have way down here at the bottom. Today, the perceptron with these feature maps is not like the hippest, coolest thing that everybody's talking about. People are talking about deep learning more than feature maps. But for the vast, vast majority of problems, certainly 99% of the problems that a company like Google encounters, if you're at a bank, then it's 100% of your problems. Feature maps are state of the art, and state of the art like by a long, long ways over deep learning techniques. The key idea of why that's sort of the case, the sort of things that we're going to be seeing relating these examples up here to our VC dimension, our VC theory, is that in general, if we pick a really good phi, what we saw above is that the training error will dramatically decrease. That we can, if you pick the right phi, you can make your training error go down to 0 in, we'll see in a little bit in every case. You can always make your training error go down to 0 if you pick the right phi value. And if you pick a phi, if you pick a feature map that has a small VC dimension, then you can control the generalization error in minus E out. The generalization error controlled by the VC dimension. And we know the generalization error of the problems we just saw. We know their VC dimension because we know the number of features. And so in particular, right here, there's only one feature. So the VC dimension is going to be 1. Up here, there were 3 features. VC dimension equal to 3. In general, the VC dimension, I'll write that below. In general, the VC dimension will always be O of D prime. Could be smaller than D prime, but it will never be larger than D prime. And so by selecting our phi so that D prime is appropriate, we can really dramatically lower our training error without making our generalization error get bad. And that'll force our true error to be good. And so we'll be seeing what I consider to be concrete examples of that in the next few pages, but it's still like abstract, not with particular like data sets, but we'll see particular phi functions in high dimensional spaces and how it adjusts these two properties. Your next actual programming assignment is going to be playing around with actual real data, doing these things and seeing that the theory stuff that we're predicting in the notes here does actually very, very closely match what you'll get with the real data sets. Any questions? Okay. So the generic feature transforms. The polynomial feature map, generalization of the examples that we saw above. And it is one of the most, if not the most popular feature maps because it's relatively simple and it's really, really powerful. The textbook devotes 5 pages to it if you want like a really, really example-focused explanation. The idea is that if we have a Q degree polynomial, we're going to use all possible monomial combinations of Q different terms. I think it's easiest to understand by example. So in 2 dimensions, a second degree polynomial feature map is going to have the x1, the x2. These are the original features right here. And then these are all the second degree terms. So the 1 degree terms are the original. And then the second degree terms are like x1 times x1, x2 times x2, x1 times x2, all possible combinations of 2 different of the original variables. The third degree polynomial has the original plus the second degree things plus all the third degree combinations. So x1 times itself 3 times, x2 times itself 3 times, x1 squared x2, x1 x2 squared. And so down here, how does the choice of Q affect our training error? Well, in particular, if we have that, let's make sure I write this correctly. If we have 2 different polynomial feature maps, say Q and Q prime, where Q is greater than Q prime, then H of phi of Q, so the feature, the perceptron using the feature map of Q dimensions is going to be a superset of the perceptron of phi of Q prime dimensions. We can see that by example up here with phi2 and phi3, that all the features up here in phi2, all the features up here in phi2 are contained inside of phi3, but phi3 also has some additional features. Phi4 will contain all these ones, plus even more additional features. So as you increase the degree of the polynomial, you're only adding more new features that you're considering. And we've seen this relationship before, that if we have, we'll call it GQ is our learned thing in there, and GQ prime is our learned thing in there, then the En of GQ must be less than or equal to the En of GQ prime. And so adding more features is just going to, it can't make our training error worse. There's, in fact, we can say an even stronger statement called the universal approximation property about the polynomial feature map. And that's that in the limit, as Q goes to infinity, so as you make your polynomial like an infinite degree polynomial, then the training error of G sub Q is going to be equal to 0. So no matter how complicated your training data set is, there is some polynomial that is sufficiently large enough that that we can exactly represent that that data set. Another way of saying that is that well, let's see. GQ trained on infinite data with infinite Q. So there's a sort of informal statement right here, is going to be equal to our F function. If you have infinite data and infinite Q, we can get our GQ to be arbitrarily close to F. Formalizing that statement requires a bunch of super awkward real analysis, but that's the intuition that that you can get your function to be as close as you want to any other function if you have infinite data and infinite dimensions. This, I don't know, may seem like a really powerful thing, but you've seen something very similar to this in Calc 2 with Taylor's approximation theorem, that the polynomial kernel is like a Taylor approximation. Just the multivariate version. And so you went through probably a long time ago about how polynomials can approximate an arbitrary function in one dimension. And it turns out to be true in higher dimensions as well. So there's another reason why this is a very popular kernel, because no matter what your function is, your true function, you can, with an appropriate polynomial, approximate it well. Any questions about any of that? Okay. So this, the previous two questions are questions about the training error. And it's good to have a low training error, but we also need to have a low generalization error. And what we have, our tool for controlling the generalization error is the VC dimension. You should always be thinking in your head about if somebody's only talking about the training error, then you should be suspicious about what is their VC dimension. Is that getting too large? And if somebody's talking about the generalization error, you should be thinking about, I want to know exactly what that VC dimension is, because the VC dimension tells me what the generalization error is going to be. And so this problem number 3 now is about the VC dimension. And it turns out the formula for the VC dimension, something that would be a fun discrete math exercise to prove how many, in a multivariate polynomial, how many terms are there. Skipping all of that, the answer is Q plus D, choose D. So this is that choose notation, which is also equal to Q plus D factorial divided by Q factorial D factorial. So this is our formula for the VC dimension. A little bit awkward to work with like this, but if we fix D, so don't let D go to infinity, this formula holds for all possible values of Q and D, but if we fix D, let Q go into infinity, then dVC equals big O of, make sure I write it correctly, Q to the D. If we let D equal Q, both go to infinity, then the VC dimension is lower bounded by 2 to the D. So let's talk about those, the meaning of these two things here for a second. Up here we have a polynomial bound, Q raised to the D. Polynomials, anytime we're in any sort of thing remotely like computer science related, we love polynomials. They are nice and they're fast for runtimes. They give us good generalization bounds for VC dimension. And in particular here, oops, I got my, oh yeah. In particular here, this is going to be a small, like a small degree polynomial. So like if D is 3, then this polynomial over here is like to the cubed. And so that's not too bad. This thing down here, though, is a lower bound. It turns out that factorials grow faster than exponential. And so omega of 2 to the D, that's like horrendous growth rates. You're never going to have 2 to the D data points for something. And so you can't let both your Q and your D's go to infinity. You have to fix one of them and only let the other one grow. Yes.
What do you mean it's like horrendous?
What do I mean that it's horrendous? That if you plug in like really small values, like Q and D both equal to 5, like that's a seemingly smallish data set, then this value over here is going to be something like 10,000. And if you go up to like 10, then this value over here is going to be in the billions. This is our VC dimension, and the number of data points that we need is proportional to the VC dimension. And so if our VC dimension is in the billions, then we need billions of data points. Again, your next programming assignment is going to have you playing around with this. You'll be creating plots of these different VC dimensions and training models with these different VC dimensions. And you'll see that as you have that absurdly large VC dimension, then things do not work well. Your training error will be fantastic, but your generalization error will not be fantastic. Good question. Any other questions? Yes. So anytime somebody's talking about the like bragging, I have really good training error, then you should be thinking in your head, okay, training error is not enough. You also need good generalization error. And generalization error is synonymous with VC dimension. Our VC theorem states that that as the VC dimension goes up, the generalization error also goes up in proportion. And so we want to keep this VC dimension as small as we can somehow in order to keep our generalization error small.
Why does training error matter then? Because if we care about generalization error, how it forms out of sample.
Yeah, so great question. Ultimately, this leads us down here. What we care about, E out is the thing that we care about. So E out is equal to E out minus E in plus E in, just by adding and subtracting E in. This is our generalization error. The VC dimension controls this. This is our training error. This is the thing that we can actually measure, that we actually know. And so if our training error, the question is, why does training error matter? Well, if we can force our training error to be really, really small, like 0, and maintain our generalization error also being small, then that guarantees that our true error is going to be small. In general, E out will always be strictly greater than E in with high probability. If you get like really lucky on your sample draws, then this might break down. But this is basically always the case. Certainly in practice, it's always the case. And so if our goal is to make this E out as small as we possibly can, then we would want to use the polynomial kernel. So say use it when E in is large, because one of the things about the polynomial kernel is we can drive E in all the way down to 0 if we want. We can get it as small as we want. But at the same time, our number of data points in is also large, or in proportion with what our final VC dimension is going to be. So D prime is the final VC dimension. And as long as those two things remain proportional, then our generalization error up here will stay constant with what it was before, but will decrease this term, resulting in E out also decreasing. This key thing for all of these, oh, it looks like it. Sorry, yeah, I wrote out polynomial kernel here. Again, kernel synonymous with transformation feature map. Normally, I would call all of these things kernels. But this is the ultimate thing that you want to know about each one of these these feature maps is when do you use it, why do you use it, in what situations. And in order to know when you use it in what situations, you have to understand how does it affect my training error, how does it affect the VC dimension. Any questions on that? Sure. So the most important thing for any of these feature maps is how does it affect the, like when do you want to use it, under what situations? And in order to know the situations that you want to use it, you have to know when does it decrease my training error, and how does it affect the VC dimension, or how does it affect the generalization error? So for each one of these feature maps, these set of questions always start off with like, how does it affect training error? Then how does it affect VC dimension? And then at the end, based on those things, conclude when you want to use it. Let's see. We have a little bit of time to start on this PCA feature map, another very, very famous feature map here. This is an example of what's called a linear feature map. It's linear because this down here is a linear function. So linear feature map. One property of linear feature maps is that the VC dimension can never go up on a linear feature map. So the VC dimension can only decrease on these linear feature maps. This A matrix right here is unique. So every linear feature map is going to have a different one of these A matrices. In the PCA feature map, it's defined to be, you compute this X transpose X matrix, and then calculate the top K eigenvectors of this X transpose X matrix. It turns out that those eigenvectors select what's called the subspace with maximum variance. We're not going to talk in detail about why that's the case in here. That's sort of a linear algebra question. And I think, let's see, so I have this big note down here, this big paragraph. The idea of this paragraph is that if you're on like technical interviews with people, it's very common to ask about like how PCA works. And it's very common for people to expect the explanation to somehow involve this statement of maximum variance and explaining why it's the maximum variance. But that actually doesn't like matter in practice because it doesn't affect any of the statistical properties. That without talking about that, we can talk about all of the different statistical properties about PCA, how it affects your training error and your generalization error. And those are the only things that you care about. Yeah, again, in this course, for the purposes of this course, not going to talk about the idea of maximum variance, but for interview preparation, that would be something that you would want to know. So the first question here, how does this K affect En? And so first of all, if K happens to be equal to D, then that'll imply that the that K is also equal to D prime, and our feature maps, the VC dimension is always O of D prime, and in this case, it's actually going to be that it doesn't actually do anything to the data. The data will look different, but the perceptron will give you the exact same result on it. And so the En of G phi will be equal to the En of G. Here, the G being trained on the non-transform data. Original data. And this G phi trained on the transform data. And exactly seeing this is, again, a exercise in linear algebra that we're not going to go into the details of, and you can take it as fact. But as k decreases, that will somehow imply that the size of h phi also decreases, which will imply that our training error increases. So again, the intuition about our training errors is somehow that whenever you're using a smaller hypothesis class, a hypothesis class that is a subset of some other hypothesis class, the smaller hypothesis can only have a larger training error, can never have a smaller training error. As k decreases, we're using fewer of the resulting features, and so we're increasing the training error. The VC dimension, though, VC dimension will be equal to theta of k. And so decreasing the VC dimension will increase, so right down. K down implies the VC dimension down implies my generalization error En minus E out also goes down like that. There's a little bit more for us to talk about this PCA feature map and some of the other feature maps, which we'll get into next class period on Monday. We'll also talk about on Monday your next programming assignment, which will hopefully make all of this more concrete. This is a good stopping point for us for today. So if you're happy to answer questions if you have them. But otherwise, that's it for today.